Morning. Session, I would like to demonstrate some simple calculations which can also be done manually. First of all, I'll be demonstrating how to calculate the standard heat of reaction by taking this particular stoichiometric reaction, followed by how to estimate the adiabatic reaction temperature for the same. Okay, so let us go ahead and see how this can be done using Aspen. So the three components that we are going to handle in this problem happen to be carbon dioxide, hydrogen, and methanol. Okay. Having selected this, you need to go into the property model. Remember, we are trying to calculate the standard heat of reaction. You know some of the conditions associated with standard heat of reaction. The reactants and products must be in their respective ideal state at a pressure of 1 bar in case of gases, okay, in their respective ideal states. So I am selecting an ideal property model. So go to simulation environment. You can see various models under reactors in this tab: stoichiometric reactor, equilibrium reactor, CSTR, plug, and so on. So I'll be starting with this. Please read that statement. Stoichiometric reactor based on known fractional conversions or extents of reaction. So you can see once again that this is also a simplified model which can be used while performing the initial mass and energy balances. This will not be identifying neither the type of reactor nor the kinetics are required, and it will not be trying to calculate or design the type of reactor or the reactor details. But it will be able to perform, given the conversion or extent of reaction, you will be able to perform the mass balances and energy balances. So having drawn this flow sheet, let me go into the next step. Now you know standard heat of reaction I would like to calculate at a temperature of 25 degrees centigrade, so that whatever value that you are computing here can be also compared with your conventional calculation utilizing the heats of formation which are normally available at this 298 Kelvin. And the pressure has to be 1 bar because it is one of the conditions associated with ideal state. And the mole flows, they must be in the stoichiometric ratio. So if they are not in the stoichiometric ratio, we will not be able to call it as standard heat of reaction. Okay. This is, we have defined the stream. Now let us go to the next input screen. Once again, because we are trying to calculate the standard heat of reaction, the reactor also must operate at the same conditions. Go to the next. We need to define the reactions stoichiometry. Now you can see on the left hand side you are defining reactants, on the right hand side you are defining products. So select the components that we have already defined. Now the stoichiometric coefficient for this reactant CO is 1. Please observe the change when I click it outside. This is again as per the thermodynamic notation. The stoichiometric number will be negative for all reactants, whereas in the case of products it would be positive. Hydrogen again 2H2, and the product is methanol 1. Now what is the conversion? So if you are calculating the standard heat of reaction, the fractional conversion should be 100% or 1 with respect to any component. Let me select CO. Because they are in the stoichiometric ratio, if 100% conversion is happening with respect to CO, 100% hydrogen also will be converted. Next. Now you can see the required input is complete. We should be in a position to run the problem. But let me go into this heat of reaction. We wanted to calculate the report calculated heat of reaction with respect to reaction number 1. The reference component, I am selecting it as CO at this temperature and pressure. Right? Next. Okay. I think you will be able to see the stream summary. Temperature and pressure are constant. The mole flows, 100 moles and 200 moles of methane are entering, but they are completely converted, giving rise to the formation of 100 moles of methanol, the product. Similarly, you can also see the balance. So the mole and energy balance is addressed. Once again, you can see a significant change in the energy balance. Why is it so? We are operating the reactor at a constant temperature of 25, depending on whether the reaction is exothermic or endothermic. In order to maintain the temperature at the same level, you either need to add heat or remove heat, right? Of course, we can see that from the other details, the heat duty of this exchanger. Now you can see heat duty is negative. What do you mean by that? This reaction is exothermic. Unless and otherwise you remove this much of heat, it will not be possible for you to maintain the temperature at the same level, right? So we can calculate this. But what about reactions? So you can see the heat of reaction has been computed as 21,594 calories per mole, right? So this is the standard heat of reaction because we are trying to maintain the conditions in the respective states required for calling this heat as standard heat of reaction. Just one question from my side before going to the next problem. Let me go back to this. You remember what was the heat of reaction that we just now calculated? 21,594 or so. Now I would like to slightly modify this and if I try to calculate the standard heat of reaction now with respect to hydrogen, what will happen? What will happen to the standard heat of reaction? Will it remain the same at 21,594 or will there be any change? So try to please check up the definition of your standard heat of reaction. You can see the value of this heat of reaction. Sorry, I need to look into the results, not definition. Now it has practically become half. Why is it so? Remember, the standard heat of reaction is always defined based on unit mole of that particular reactant converted. See, for every mole of carbon monoxide converted, you know, as per the stoichiometry, 2 moles of hydrogen are converted. But the amount of heat liberated due to this reaction remains the same. So if you want to find out the heat of reaction with respect to hydrogen, the heat of reaction becomes half compared to the heat of reaction on the basis of carbon monoxide. Please convince yourself about this. Let me also switch to the second problem. In this, we have calculated the standard heat of reaction. Probably you can compare this result calculated from standard heats of formation. Now I would like to calculate the adiabatic reaction temperature, same stoichiometry, but we are assuming that the conversion with respect to CO are the only changes, right? So let us go back. Will I be able to calculate the adiabatic reaction temperature? The temperature attained by the product stream when you operate the reactor under adiabatic conditions can be called as adiabatic reaction temperature. Earlier, we were operating this reactor at a constant temperature of 25, but we need to operate this under adiabatic conditions. So instead of defining temperature, let me call it as duty and deliberately say this as 0. I don't want to either add heat or remove heat. So you can consider this to be under adiabatic operation. So this is one change. Of course, in the case of reactions, instead of 100% conversion, we were given percent. So this is another change. Right? So you can once again look into the problem statement. Same reaction stoichiometry. They are in the stoichiometric ratio. Temperature and pressure are the same. Conversion instead of 100, we were given as 80. Under these conditions, we are reaction temperature. So let us run this problem. Okay. Now you can look at the stream summary. Now you can see the inlet temperature was 25 and the outlet temperature was 949. Can we call this as adiabatic reaction temperature? Why the temperature is increasing? Because we are not trying to remove heat. The heat liberated due to reaction, we already saw it is an exothermic reaction. The heat of reaction is negative, which we just now calculated in the previous case. So the heat liberated is not removed, so that is going to increase the temperature of the product stream. So this can be considered as the adiabatic reaction temperature. Now try to see how you would have calculated this adiabatic reaction temperature manually. Okay, just I'll leave it to you, which you might have been doing. Now the second part of this problem is what will happen to this adiabatic reaction temperature if CO and hydrogen are in the mole ratio of 1:10. Earlier we were using CO and hydrogen in the ratio of 1:1. Now we would like to use it in the ratio of 1:10. So let me go back and modify this as well. So let me keep the CO flow rate at 100, but it is now, instead of 200, it is entering 10 times, 1:10 ratio, right? So with this change, what will happen to your adiabatic reaction temperature? What do you expect? Will it increase or decrease? So you should be able to analyze the problem, in fact, before looking at the results. Now you can see the temperature came down to 271. Why is it so? So even when all the 80% of carbon monoxide is converted, the amount of heat liberated will be similar to what you had seen in the previous case, right? Now the same amount of heat has to be utilized to heat a larger amount of fluid, reaction mixture. Now there is a lot of hydrogen. That's why the temperature is coming down. In fact, this is normally one of the cases which can be used. The excess reactant is going to maintain the temperature increase, or is going to regulate the temperature increase. But remember, if you have highly exothermic reactions, normally we'll be either adding one of the reactant in excess or add some kind of an inert to increase the mass so that the temperature increase is under control. But what is the penalty that you may be looking at? From the product stream, the excess reactant need to be recovered. So the separation costs are going to increase. So you need to, in fact, balance both these. The benefit that you are able to get in order to control the temperature is on one side, and the extra cost that you need to spend in order to recover your product from a large material, right? So this could be some kind of an optimization issue. Now with this, again, I would like to close down my session.